What is then the k-means objective that we're trying to optimize here? What's actually being optimized? Once again, we want to find cluster centroids M and assignments R, assignments of every data point N to every cluster centroid MK, to minimize the distance of the points to their assigned cluster centroids. So what are we doing? We're saying that we are minimizing over the choice of cluster centroid M as well as assignments R, such that the distance from every point xn to its assigned cluster centroid, summed over all the assignments, subsummed over all the instances, is minimized. And this, once again, is just a one hot vector with one somewhere, depending on the k that it's assigned to, and 0 elsewhere. Sometimes we refer to the objective as the inertia or total variation. Depending on the choice of D, we can refer to it as either one of these. How do we go about optimizing this function? This function, the j of m and r, is a multivariable function. And minimizing it requires special care, and there's algorithms like block coordinate descent that can do this optimization for us. But really, the way that we do it ultimately is the iterative process of starting with some initial set of centroids, doing assignment, and then doing updating of centroids, and iteratively going through that until it converges. That's also what block coordinate descent does for us. Now, one question here. Yes, Farsa?
So sorry, is block coordinate descent going to derive like a closed form solution for the optimization, or do we have to perform this iteratively?
That's a very good question. No, block coordinate descent, in its name, it means that we descend on every coordinate independently, or every block of coordinates if there's more than one,
Okay.
in groups. And no, it's still an iterative process.
Okay.
Very good question. Now, just for terminology's sake, I said that J is a multivariable function. This is different from having a multi-objective optimization. What's the difference between these two? Multivariable optimization versus multi-objective optimization. Where have we seen multi-objective optimizations before? Remember earlier we had minimize over some parameters w of a loss of y and t plus lambda of r of w, something like that. For instance, for linear regression, where we wanted to have regularized weights, this was a multi-objective optimization function, or in this case, it was a constrained optimization written in Lagrangian form as a multi-objective optimization. But this is not, there's only one objective we're trying to minimize, and that objective is the sum of the distances of every point to its assigned cluster centroid. So there's only one objective, but it's multivariable because it's over different variables. And so these variables are also dependent on one another. If they were independent, that would be a different story. But because they're dependent on one another, then we have to go through an iterative process. Yes? Cool? Makes sense? Excellent. So now to Shima's question about convergence. And I'm only going to present a high-level intuitive argument, but it turns out that we have some guarantees in this iterative process, and that guarantee is that the loss will always go down. Why does the loss always go down? Because we're iterating between two steps. The first step is the assignment step. By definition, the assignment means assign every data point xn to the closest centroid that is available for us. Closest centroid means that distance is going to go down. Right? So that one we understand. And then the update step says, with the assignments fixed, we're going to move the cluster centroids to the mean of all the points assigned to it within that centroid. And I'll leave this as homework for those who are interested, but if you move to the mean point of any groups of points minimizes the sum of distances between the mean and those points. So let me maybe draw it out. If I have a number of points like this, and if I assume a cluster centroid here, then this d1, d2, d3, and d4, sum of di squared for this m, and any m other than the m which is the mean, is going to be larger than sum of di squared for m star. So the mean point minimizes the sum of distances squared from all points in a cluster assigned to that mean. And similarly, the median point minimizes sum of distances, but not sum of distances squared. Okay, so back to the argument then. We have an iterative process where we make assignments, and assignments by definition are find the closest centroid, so that reduces the distance. And then we have the update step, which moves the mean, and that the mean is the point which minimizes sum of square distances to the cluster points. So yes, Shima is absolutely correct that we can look at a loss curve over different iterations, and we'll see that the loss curve always goes down. It's convex. In parentheses, it's dependent on the initial centroids. So it might or might not arrive at the optimal point. It might not always follow the same path, but every initialization has its own convex loss, which definitely goes down through the iterations. And our test for convergence is, once again, same as before, that if the assignments do not change, then we have converged at least to a local optimum. And you'll see here that we have two different steps. We have the update step and we have the assignment step in different colors. And you'll see that if the loss does not change, that means we've already converged for this choice of data, this choice of number of centroids, and this choice of initialization of those centroids. Okay, so we have a couple challenges to deal with. The first one is a bad local optimum, or a bad local optimum due to a bad initialization. We said that since our objective is multivariable and non-convex, the objective itself is non-convex, coordinate descent on J is not guaranteed to converge to the global minimum. And here is an example on the slide with maybe 2 clusters or 3 clusters. Let's say that the clusters are actually these ones here. But I can come up with an example of initial centroids such that we get to, a combination which doesn't look optimal to anyone. So how would you go about resolving this situation? What do we think?
Add some noise, possibly.
Okay, that's actually very clever, right? So add some noise at different points.
Yeah.
There are various algorithms within optimization, even for gradient descent on neural networks, where noise is super important because of things like this. If we get stuck somewhere that's not so optimal, right? And then there's trade-offs. We have another hyperparameter. Maybe noise is too much at some point, so there's trade-offs. But that's a really interesting solution. Yes, Hamza?
Tempted to say to repeat it multiple times and then take the average of the solution, and then once you have the average of the solution, take that as your initial starting point.
Okay. Wow, that's also a clever solution. So instead of just doing it once and arriving at this local optimum, just do it multiple times and then see the average solution. Use that as another. Okay. Maybe let me simplify Hamza's suggestion a bit and say we could run it multiple times and just take the best one in terms of the final distance or the final initial value. Right? We could do that. It sounds silly, but if our algorithm is so sensitive to the initial points, then that's what we should do. Also, that's what you should do for a small neural network with not a lot of parameters. Typically, neural networks have so many parameters that their loss landscape is so high dimensional that it's really hard to characterize, and you don't need to run multiple. But it's actually common in training of neural nets to run it multiple times just to see which one gives you the best answer. That's why we always store the seed, right? The seed that gives us the random initial points. So yes, possible solutions include. I really like the noise one. I should add this to the slide. Add noise. So we could try multiple runs of k-means with random starting points. We could also try more complex strategies, like at various points within the iterative process. If we see 2 centroids are very close to one another, then we can merge them somehow. Those are extensions of k-means. Or if we see one centroid with a very large distance of points assigned to it, then we can split it off into, these are, of course, extensions that one can apply with their own set of trade-offs. Yes, Pars?
So you said we can, I guess, optimize multiple times and then reuse the optimizations as initial points. Are those what epochs refer to in neural networks, like epochs of training, or is that like an example I'm just trying to understand what like epochs are and how they relate.
Right. So that is not epochs, at least not based on my understanding.
Right.
Epochs in neural networks just mean one forward and backward pass
Oh, okay.
over your gradient descent steps.
Right.
Now,
Okay.
there's an addendum there as well as to whether you're doing batch gradient descent or stochastic gradient descent. I'll not go into that. But this suggestion that we run it a bunch of times and maybe use that as the initialization for some n+1 time, I haven't heard that being called epochs.
Okay. Thanks.
Okay, so this is our first challenge, local minimal. We have yet another challenge, which we started off with initially, which was, what is what you mean by the elbow method?
Yeah, sorry. Yeah. So for the elbow, it's basically you pick the smallest k, and then you keep on increasing, and you track what is the best loss that you get for that number k. And when you see that there is no, I mean, there will always be an increase in the loss. Like, I mean, eventually it gets to 0, right? If you get k equal to the number of samples, then like each sample is its own centroid, right? So the distance is 0. So it will get to 0, but it's also a bad solution. So basically, you start from one cluster, and then you keep on increasing k. When you see that there is not much decrease in the loss, that's your k, and then it looks like an elbow basically. So you look at these points of like a source of.
So Hamza is basically your cheat code in this class, because he's just giving you every answer. But we'll go through his answer one by one. So yes, the elbow method says that I'm going to run k-means clustering for a range of values of k, starting from a small value of k up until a large one. Yes? And then I'll keep track of the inertia, the sum of distances, squared distances for each of those values of k. And at some point, we're going to see big drop, big drop, big drop, not so big drop, and etc. So diminishing returns in the drop and loss as k increases. This is not a good figure, because this suggests that the loss goes up. The loss does not go up for the best choice of initialization of every k, but it is an elbow if it's not extending upwards. Anyways, bad figure. But yes, that we choose, and this is a heuristic, the point at which we sense that increasing the value of k no longer gives us the returns that we'd like to see in terms of loss drop. Hamza is claiming that at some point, for some value of k, the loss is 0. Why is that? And which point of k is that? The answer is on this. Okay. Yes, Mohammed.
I guess when you have a segmentation for every single possible choice.
Right. So if you have k equals n, what happens when you put each data point into its own class? Then, of course, the distance will be 0, and the centroid point and the data point themselves overlap, and so you have the loss equals 0. But when does that happen? That only happens if you've done proper initialization. Right? You could have a poor initialization that either doesn't converge or there's too many points for it to actually be tractable, and it won't actually get to the point where every centroid becomes that. I mean, the naive solution is just to initialize each of your centroids to each of your data points, and then there's nothing to do. There's no algorithm. You just stored your entire data set. So all of this is silly gabbly-goop conversation, but really there is some point at which, not for any initialization, but for the best initialization at k equals n, the loss will be 0 trivially. So for k equals n, the global minimum of the loss is 0. However, there's no guarantees that the randomly initialized centroids will ever find that global minimum. And practically useful anyways. What's the point of having the same number of centroids as data points? You just have your data set to begin with.